Exercise 4, Designing Superelevation. Design the superelevation transition for a curve with the following parameters. We have a 4-lane divided urban principal arterial. Roadway is rotated about the inside edge of each roadbed. The PC station is 10 plus 00. The design speed is 50 miles per hour. Degree of curvature is 3 degrees, and the original normal crown is 2%, and the ADT is greater than 400. For the roadway being rotated about the inside edge of each roadbed, we have the following diagram. You can see that the roadbed is being rotated about the inside edge, and that in this scenario we have a 2-lane rotated highway. What is the runoff length? The Emax 4% table should be used because it is an urban facility. Below is a table of the Missouri Standard Plans 203.22, page 1 of 2. On that Missouri Standard Plans, there are 2 tables. The table that we have listed below is the Emax 4% table. Let's calculate the radius r. The equation 5,729.58 divided by d, or the degree of curvature, will calculate our radius. If we plug in the numbers, we get a radius of just under 2,000 feet. If we look on the chart under the 50 mile an hour columns, we look at the radiuses, we'll notice that the radius of 1,909 feet falls in between 2 values. When this happens, you take the more conservative value, which is the 3.4% E rate. So Emax from this table is going to be 3.4%. The runoff length is going to be 122 feet because it's 2 lanes rotated. And does this curve need spirals? This is important because if this curve has spirals, our superelevation locations will differ from curves that do not need spirals. To determine if this curve needs spirals, we look at our standard plans 203.20G, page or sheet 1 of 4. In there's some verbiage about spiral usage. Spiral curves are used on all roadways that have a design traffic greater than 400 vehicles per day. In this example, we do have our ADT greater than 400 vehicles per day, and have a radius less than the values listed in the maximum radius for use of a spiral curve transition table. That table is also listed on that standard plan and looks like this. So if we look at our design speed, the maximum radius is 1,265. Our curve radius for this example is 1,909, so therefore no spirals are needed. What is the tangent runout length? The tangent runout is this equation found in our standard plans. X equals the normal crown times the length of runoff over your E rate. It is this distance here from AA to BB, or it can be BB to CC as well. If we plug in the values on that equation, we get 2% times 122 divided by 3.4%, which is our max E rate for this curve. We get a tangent runout length of 71.76 feet. Let's develop the superelevation transition locations. Let's first calculate the section AA station value. If we look at our standard plans 203.22, you'll get a diagram of the superelevation transitions. And we're going to be calculating the station at the section AA. So we know the PC point of the curve, and so we're going to go that distance indicated by the blue arrow. To do that, our section AA station will equal the PC station minus 2/3 L minus X, which we just calculated. If we plug in the numbers, the PC station equals a station value of 10 plus 00 minus 2/3 times 122 feet minus 71.76. For the value at for the station value at section A, we get 8 plus 46.91. Now let's calculate the section BB station value. So we just calculated the station value at AA, so all we have to do is go up a value of X to get our BB station. If we plug in the values, we get the following. And for our BB station, we get 9 plus 18.67. Now let's calculate the section DD station value. Again, if we look at our standard plans 203.22, sheet 1 of 2, the figure, there are a number of ways we could calculate the DD station. The way that we're going to do is we're going to take our BB station value that we just calculated and we're going to add L. So if we plug in the numbers, we take our BB station that we just calculated plus 122 feet. So our DD station value is 10 plus 40.67. Similar to developing superelevation at the beginning of the curve, transitions must be designed at the end of the curve as well. This time we're going to transition from the full super back down to a normal crown. If the PT station is 13 plus 60.34, let's calculate the stations for the superelevation transitions. The full super starts transitioning back to a normal crown at 1/3 L before the PT station. So section DD equals the PT station minus 1/3 L. If we plug in the numbers, we get the following value of 13 plus 19.67. Section BB equals section DD plus the distance L, or the runoff length. If we plug in the numbers, we get the following for the section BB of 14 plus 41.67. Section AA equals the station at section BB plus the value of X, which we calculated on the previous slide. If we plug in the numbers, we get a station value for AA of 15 plus 13.43.